While you're sitting in your chair reading these exact words, an invisible monster across the cosmos is violently churning the fabric of reality itself. It is heavier than millions of our suns combined, yet it is whirling so fast that the outer edge of its dark heart is nearly matching the ultimate speed limit of the universe. Time and space around it are being dragged into a dizzying cosmic whirlpool from which nothing can ever escape. This is not science fiction or computer glitch. It is a real place discovered in deep space right now. If you love exploring the strange, real truths of our universe without any exaggerated hype, make sure to hit that subscribe button right now. Join our community of curious thinkers who love real science so you never miss another deep cosmic discovery. To understand why this discovery left astronomers completely speechless, we have to start with what a black hole actually is. Imagine taking something with enormous mass, like our entire planet Earth, and squeezing it down until it fits inside the size of a tiny marble. If you did that, the gravity on that marble would become so intensely strong that not even a beam of light could move fast enough to pull away from it. That boundary where light gets trapped forever is what scientists call the event horizon. For decades, most people imagined black holes as quiet, bottomless sinkholes sitting motionless in the dark corners of space. Early physics models often treated them as simple, perfectly round objects that simply waited for stray gas or wandering stars to drift too close before swallowing them whole. If you dropped something in, it disappeared, and that was the end of the story. In those early textbook diagrams, a black hole looked like a calm, static sphere floating quietly against a background of distant stars. Then, astronomers pointed some of the most advanced space telescopes ever built toward a distant galaxy billions of light years away from Earth. Instruments like NASA's Chandra X-ray Observatory and the European Space Agency's XMM-Newton satellite captured bizarre signals coming from the core of that distant galaxy. When the research teams analyzed the data, they realized they were not looking at a calm, static sphere at all. They were looking at a supermassive black hole that is spinning at over 99% of the speed of light. To put that speed into perspective, light travels through empty space at roughly 186,000 miles every single second. That means a single beam of light could wrap around the entire Earth more than 7 times in the blink of an eye. Now imagine a monstrous cosmic object containing the weight of millions of stars, with a width spanning millions of miles, whirling around on its central axis almost at that exact same blinding speed. The gap between what scientists originally expected and what they actually measured changes everything we know about how the universe grows. If a black hole spins this fast, it means it did not grow by slowly sipping on quiet clouds of dust over billions of years. Instead, it must have been fed by an unimaginably violent, non-stop torrent of colliding matter, or perhaps by smashing directly into another massive black hole in a catastrophic ancient collision. Every single revolution of that black hole holds the hidden history of an entire galaxy's violent birth. To truly understand how we got to this shocking discovery, we need to go back over 100 years to the work of Albert Einstein. In 1915, Einstein published his general theory of relativity, which completely changed how humans think about space and gravity. Before Einstein, people thought gravity was an invisible pulling force that acted across empty space. But Einstein showed that space and time are joined together in a single four-dimensional fabric called spacetime. When an object has mass, it bends that fabric just like a heavy bowling ball creates a deep dip when placed on a soft mattress. Shortly after Einstein shared his theory, a German physicist and astronomer named Karl Schwarzschild worked out the very first exact mathematical solution describing a black hole. Schwarzschild was actually serving on the front lines during the First World War when he solved these complex equations. His math described a non-spinning, perfectly round black hole that did nothing except pull things inward with immense gravitational force. For nearly 50 years, almost every scientist assumed that Schwarzschild black holes were the standard rule across the cosmos. However, the real universe is rarely static and quiet. Almost everything in space rotates, from tiny dust grains and asteroids to massive planets, stars, and entire spinning galaxies. When a giant star runs out of fuel at the end of its life, it collapses inward under the crushing weight of its own gravity. As the star shrinks from millions of miles across down to a tiny point, it spins faster and faster, exactly like an ice skater spinning faster when pulling their arms tight against their chest. Because of this basic rule of physics, called the conservation of angular momentum, nearly every black hole formed by a collapsing star or growing at the center of a galaxy must be spinning. Yet for decades, scientists could not solve the complicated math required to describe a rotating black hole. The equations of general relativity became so complex when rotation was added that many top physicists thought finding an exact answer was impossible. That all changed in 1963 when a brilliant mathematician from New Zealand named Roy Kerr did what seemed impossible. Kerr found the exact mathematical solution for a rotating black hole, which scientists today call a Kerr black hole. Kerr's equation showed that when a black hole spins, it does something far stranger than any regular spinning planet or star. It twists the very fabric of spacetime around itself, creating an entirely new region of cosmic distortion that defies our everyday common sense. Did you know that black holes could twist the actual fabric of empty space around themselves like a giant blender? Drop a comment down below if you ever learned about spinning black holes in school, and hit that thumbs up button right now if you find this cosmic physics absolutely fascinating. When matter falls toward a spinning black hole, it does not simply drop in a straight line like a stone dropped into a deep well. Because of the extreme gravity and rotational energy, the trapped gas, dust, and shattered stars get flattened out into a glowing, super-hot disk called an accretion disk. Think of water swirling furiously around an open drain before it slips down the pipe. As this cosmic material spirals closer to the event horizon, friction heats it up to millions of degrees, making it shine with brilliant X-ray light that our space telescopes can detect across billions of light years. Here is the strange part that completely caught astrophysicists off guard. If a black hole is not spinning, the inner edge of that glowing disk of gas has to stay relatively far away from the center to remain stable. In a stationary black hole, anything that crosses inside a certain distance, known as the innermost stable circular orbit, instantly loses its balance and plunges into the dark center. But when a black hole spins rapidly in the same direction as the orbiting gas, it drags space-time along with it, allowing the glowing gas to skim astonishingly close to the ultimate point of no return. The closer the gas gets to the event horizon, the hotter it burns and the faster it whirls around the center. By measuring the extreme temperature and the energetic X-ray glow coming from this inner edge, astronomers can calculate exactly how close the matter is getting to the black hole. When NASA's NuSTAR telescope and the European XMM-Newton Observatory measured the inner edge around several supermassive monsters, they discovered that the gas was orbiting right on the razor-thin boundary of the event horizon, moving at nearly the speed of light. What makes a spinning black hole so radically different from a stationary one comes down to that famous idea predicted by Albert Einstein called frame dragging. Einstein realized that space is not just an empty stage where cosmic events happen. Space is a flexible fabric that can bend, stretch, and twist. When an object with massive gravity spins rapidly, it does not just rotate inside space, it grabs the fabric of space itself and twists it around like thick honey clinging to a spinning spoon. This creates a bizarre region just outside the event horizon known as the ergosphere, named after the ancient Greek word for work. The ergosphere is shaped like an oblong pumpkin, touching the event horizon at the top and bottom poles, while bulging outward around the spinning equator. Inside the ergosphere, the twisting of space is so overpowering that nothing can remain still, no matter how powerful its rocket engines might be. Even if you were flying in a futuristic spaceship, pointing your engines directly against the spin at full throttle, the fabric of space itself would drag you along with the rotation. In this region, space moves faster than the speed of light relative to distant observers. This does not violate Einstein's rule that nothing can move faster than light through space, because it is space itself that is moving, carrying everything inside it along for the ride. Scientists originally thought that this extreme frame-dragging effect was just a neat mathematical trick on paper that might never be observed in the real universe. They believed natural cosmic drag and random collisions would keep black holes spinning at much more modest speeds. Yet when researchers measured the X-ray emissions coming from the iron atoms swirling inside the accretion disk of this newly measured black hole, they saw the light waves stretched and warped in a way that could only happen if the ergosphere was pushed to its absolute physical limits. The reason this matters so much is that a spinning ergosphere is not just a gravitational trap. It is one of the most powerful natural engines in the entire universe. In 1969, a brilliant British physicist named Roy Penrose realized that if an object enters this twisted region of space and breaks in two, one half can fall into the black hole while the other half escapes with more energy than it had when it arrived. The escaping piece literally steals rotational energy directly from the spinning black hole itself. This process, now known worldwide as the Penrose process, proves that black holes are not just cosmic destroyers that hoard energy forever. A rapidly spinning black hole is actually a cosmic battery storing an unfathomable amount of raw mechanical power in the twist of its space-time. Up to 29% of the total mass of a rotating black hole can be converted into usable energy through this mechanism, which is hundreds of times more efficient than the nuclear fusion that powers our own sun. If advanced civilizations ever exist near such an object in the deep future, they could theoretically tap into that rotational energy to power entire galactic systems for trillions of years. By launching small masses into the ergosphere and collecting the accelerated pieces that shoot back out, they could harvest clean, limitless power directly from the rotation of the universe's most extreme objects. What do you think humans could accomplish if we had access to the limitless energy stored inside a spinning black hole? Share your thoughts in the comments below and make sure to subscribe to the channel so you can join our next deep exploration into the wonders of modern astrophysics. Every measurement taken by our modern orbital observatories shows that nature is far wilder than our simplest model suggested. Astronomers calculated that the magnetic fields trapped in these spinning disks get wound up tighter and tighter, like a giant steel spring being twisted until it is ready to snap. When these magnetic lines finally twist into colossal funnels along the rotation axis, they shoot beams of superheated plasma out into deep space at nearly 99.9% of the speed of light, traveling for hundreds of thousands of light years across the cosmos. These monster jets of energy and particles have enough power to blow entire clouds of star-forming gas right out of their host galaxies. In simple terms, a black hole spinning at near light speed has the power to decide whether new stars and new planets are allowed to be born in its galaxy, or whether the entire galaxy will slowly grow dark and barren. What happens on a scale of a few million miles near the center of the black hole dictates the fate of an entire galaxy, spanning billions of trillions of miles. To truly grasp how bizarre this new discovery is, we have to look at the mathematical speed limit of the universe itself. In physics, there's an absolute maximum rate at which a black hole is allowed to spin, described by a value called the dimensionless spin parameter, often written as the letter A. A value of 0 means the black hole is completely still and not rotating at all. A value of 1.0 represents the absolute theoretical maximum, where the outer event horizon would be spinning at the speed of light. For years, many astrophysicists assumed that real black holes in our universe would never come anywhere close to that theoretical limit of 1.0. Their computer simulations showed that as a black hole spins faster, the radiation coming from the surrounding hot gas pushes back against incoming matter, acting like a cosmic brake pedal that prevents the spin from climbing too high. Most researchers expected spins to top out around 80 or 85% of the theoretical maximum. Yet the newest data from deep space observatories revealed a spin parameter exceeding 0.99. That is more than 99% of the absolute physical limit allowed by the laws of nature. The black hole is rotating so close to the edge of what physics permits that if it spun even a fraction faster, the event horizon could theoretically tear open and expose what scientists call a naked singularity. A singularity is the point at the very center of a black hole where all its mass is crushed into an infinitely small point with infinite density. Under normal conditions, nature keeps this terrifying point safely hidden behind the event horizon, meaning no information or crazy physics from the singularity can ever escape into our universe. But if a black hole could spin faster than its maximum limit of 1.0, the event horizon would shrink until it completely vanished, leaving the singularity completely exposed to the rest of cosmos. Einstein's theory of general relativity suggests that a naked singularity could break our fundamental understanding of cause and effect, potentially allowing things like backwards time travel, broken laws of physics, or paradoxes that destroy the logic of the universe. That is why the late physicist Roy Penrose proposed the cosmic censorship hypothesis, which states that nature always puts up a one-way horizon to hide singularities from view. By finding a black hole spinning at 99% of that limit, scientists are watching nature balance on the razor edge of that cosmic rule right now. Think about what it would feel like to stand near such an object if you were protected by an indestructible shield. Because the black hole is spinning near the speed of light, time itself is dramatically slowed down compared to the rest of the universe. If you spent just 5 minutes floating inside that twisted space, thousands of years could pass by for everyone back on planet Earth. When you finally returned home, civilizations would have risen and fallen, and continents would have shifted, all while you barely aged a single breath. The extreme spin also changes the shape of the black hole's shadow. When the Event Horizon Telescope collaborated across the globe to take the first real pictures of black holes, they confirmed that a spinning black hole does not cast a perfectly round shadow. Instead, the intense rotation squashes the shadow on one side and creates an asymmetrical crescent of blinding light, where matter moving toward us appears far brighter than matter moving away. If you had a time-traveling spaceship that could survive near the edge of a spinning black hole, what future year would you want to jump to? Leave your destination year in the comments, and don't forget to tap that like button to let YouTube know you want more real science breakdowns like this. The story of how we discovered these extreme spin speeds is just as incredible as the black holes themselves. Because black holes emit no light of their own, scientists cannot simply point a standard visual telescope at the sky and watch them spin like a top. Instead, they have to act like cosmic detectives, studying the behavior of iron atoms caught in the surrounding death spiral. When iron atoms are superheated by friction, they emit a very specific wavelength of X-ray light that acts like a fingerprint. Under normal conditions in a laboratory on Earth, this iron fingerprint produces a sharp, narrow spike on a sensor. But when astronomers pointed their satellite instruments at these distant spinning monsters, they saw that the iron spike was stretched out into a broad, distorted curve. Part of this distortion happens because the gas is moving toward us and away from us at near light speed, causing a Doppler shift. But the rest of the distortion is caused by gravitational redshift, where the immense gravity of the black hole literally robs the light waves of their energy as they try to climb away. By measuring the exact shape and width of this distorted iron line, astrophysicists can calculate exactly how close the inner edge of the gas disk is to the event horizon. Because only a rapidly spinning black hole allows that gas disk to stay stable so close to the center, the width of the iron line reveals the precise spin speed of the black hole. When teams at institutions like the Harvard-Smithsonian Center for Astrophysics and the University of Cambridge ran these calculations, the numbers consistently pointed to near light speed rotation. What makes this even more fascinating is the debate over how these objects reached such extreme speeds in the first place. There are two leading theories in astrophysics today. The first theory suggests that the black hole experienced coherent accretion, meaning it swallowed a massive, steady stream of gas that all rotated in the exact same direction over millions of years, acting like a hand continuously pushing a playground merry-go-round faster and faster. The second theory suggests that two giant galaxies, each carrying a supermassive black hole at its heart, collided in an ancient cosmic smash-up. As the two galaxies merged, their central black holes spiraled toward each other in a dance of pure gravity, eventually slamming together into a single giant remnant. If the two black holes were spinning in alignment when they merged, their combined rotational energy would create a new supermassive giant spinning at the absolute brink of light speed. Right now, giant gravitational wave detectors like LIGO in the United States and Virgo in Europe are listening for the faint ripples in spacetime caused by these colossal collisions across the universe. Every time two black holes merge, they send out gravitational shock waves that stretch and compress the entire planet Earth by less than the width of a single subatomic particle. By decoding these cosmic ripples, scientists are beginning to map out the spin history of black holes from the earliest eras of the universe. This ongoing research proves that the universe is not a finished painting hanging on a museum wall. It is an active, evolving laboratory with extreme experiments running in real time. Every new measurement from our space telescopes brings us closer to understanding the violent origins of the supermassive black holes that sit at the core of nearly every large galaxy, including our own Milky Way. To understand why this is so critical right now, we have to look at the supermassive black hole sitting at the very center of our own Milky Way galaxy, named Sagittarius A star. Sagittarius A star contains the mass of over 4 million suns, packed into a region smaller than the orbit of Mercury. For a long time, scientists wondered whether our own galaxy's central monster was spinning quickly or resting quietly in the dark. Recent studies using the Event Horizon Telescope and NASA's Chandra Observatory suggest that Sagittarius A star is also spinning at an astonishing speed, estimated to be between 84 and 96% of the speed of light. This means that even right in our cosmic backyard, space is being dragged around in a violent gravitational vortex. Although our solar system is located at a safe distance of about 26,000 light-years away, the spin of our central black hole has played a massive role in shaping the spiral arms of our galactic home. Which of the two theories do you believe created these near-light-speed spins? A steady stream of gas over millions of years, or violent collisions between two giant black holes? Cast your vote in the comments section below, and click that subscribe button right now to stay connected with our growing science family. Let us explore what happens to the matter that gets caught in this cosmic blender. As gas spirals inward toward a near-light speed black hole, the friction between neighboring layers of gas generates temperatures exceeding tens of millions of degrees. At these extreme temperatures, electrons are stripped away from atomic nuclei, creating a glowing state of matter called plasma. This plasma does not just glow with visible light, it unleashes blinding torrents of ultraviolet radiation, X-rays, and gamma rays. Because the black hole is rotating so quickly, the magnetic fields threading through this plasma become tightly coiled like a giant corkscrew. These coiled magnetic fields channel a huge portion of the incoming plasma toward the poles before it ever crosses the event horizon. Instead of being swallowed, this matter is blasted outward into intergalactic space in narrow, focused beams that can travel across millions of light years without spreading out. These beams, known as relativistic jets, carry so much kinetic energy that they can heat up the gas clouds surrounding entire galaxy clusters. In many giant elliptical galaxies, these jets act like a galactic thermostat. Whenever too much cold gas settles into the center of the galaxy, the black hole feeds on it, spins up, and fires powerful jets that heat the surrounding gas back up, preventing it from collapsing to form new stars. When the gas warms up and stops falling inward, the black hole starves for a while, cooling the system down until the cycle repeats. Astronomers call this balance active galactic feedback. and it is one of the most important processes governing how galaxies grow, age, and change over billions of years. Without this delicate feedback loop driven by spinning black holes, galaxies across the universe would have produced far too many stars early on, burning through all their fuel and leaving the modern universe full of dead, dark stellar graveyards. The physics becomes even more mind-bending when you look at the structure of a spinning singularity itself. In a simple, non-spinning Schwarzschild black hole, the singularity is mathematically described as a zero-dimensional point of infinite density. But in a rotating Kerr black hole, the rotational forces prevent the mass from collapsing down to a single point. Instead, the mass is thrown outward by centrifugal forces into a two-dimensional ring of zero thickness, known as a ring singularity. Because the singularity is shaped like a ring rather than a solid point, theoretical physicists noticed something truly shocking in Kerr's original equations. If an explorer could theoretically pass through the center of the ring singularity without touching the ring itself, they would not be crushed by infinite density. Instead, the math suggests they might pass through a cosmic tunnel into an entirely different region of spacetime, or perhaps into an alternate universe. However, most physicists warn that real-world quantum effects and intense gravitational instabilities would likely destroy any traveler long before they could slip through the ring. The interior of a real black hole is filled with infalling radiation that gets blue-shifted to infinite energy near the inner Cauchy horizon, creating a lethal wall of fire that would vaporize any spaceship in an instant. Yet the mere fact that Einstein's math allows for the concept of a ring singularity shows just how strange nature becomes when extreme gravity meets near-light-speed rotation. In addition to ring singularities, rapid spin completely alters how black holes interact with quantum mechanics. In the 1970s, the famous physicist Stephen Hawking proved that black holes are not totally black. They slowly leak tiny amounts of heat radiation over time, now called Hawking radiation. For a standard black hole, this quantum evaporation process takes uncounted trillions of years. But when a black hole spins at near light speed, its surface gravity changes, altering the temperature of the horizon and modifying how it slowly evaporates into the cold void. Furthermore, spinning black holes can experience a bizarre wave phenomenon known as superradiance. If an electromagnetic wave or a gravitational wave strikes the rotating ergosphere at just the right angle, the wave can actually bounce off with more amplitude and energy than it had when it arrived. The wave steals a fraction of the black hole's rotational energy, acting like a cosmic amplifier that turns faint signals into blazing cosmic beacons. Scientists have even suggested that if a cloud of ultralight exotic particles surrounds a spinning black hole, superradiance could trigger a runaway instability called a black hole bomb. In this wild scenario, the particles would bounce back and forth inside the ergosphere, extracting more and more rotational energy until the entire cloud erupts in a massive burst of gravitational radiation. Detecting these signals could soon provide our very first direct proof of dark matter particles that have eluded physicists in Earth laboratories for decades. Have you ever heard of a ring singularity, superradiance, or the idea of passing through a black hole into another universe before today? Tell us what you think in the comments below, and if you are enjoying this deep dive, take a quick second to hit that like button and share this with your friends. Another mind-blowing aspect of near-light-speed black holes is their ability to produce intense gravitational lensing effects. Because the black hole warps space so violently, light rays passing near it do not travel in straight lines. Light coming from distant stars behind the black hole gets bent around both sides, creating multiple distorted images of the same background object, or even wrapping the light into a glowing circle known as an Einstein ring. When the black hole is spinning at 99% of light speed, this lensing effect becomes lopsided and asymmetrical. Photons of light traveling in the same direction as the black hole's spin can pass much closer to the event horizon without falling in, while photons trying to travel against the spin are pulled inward from much farther away. This causes the surrounding halo of light to warp into an eye-shaped swirl that changes in real time as matter orbits the center. Modern supercomputers require weeks of continuous processing time just to simulate the path of light rays orbiting a Kerr black hole. When NASA released high-resolution computer visualizations of these spinning monsters, millions of people around the world were stunned by how alien and mesmerizing they looked. The top of the accretion disk appears bent over the back of the black hole, while the bottom of the disk appears tucked underneath, because the black hole's gravity bends light from behind itself directly into our line of sight. Scientists are now designing next-generation space telescopes, such as the Habitable Worlds Observatory and the LISA Space-Based Gravitational Wave Interferometer, to study these extreme gravitational environments with unprecedented precision. LISA, which will consist of 3 spacecraft flying millions of miles apart in a giant triangle, will detect low-frequency gravitational waves from supermassive black holes merging across the cosmos, giving us a front-row seat to the birth of these near-light-speed giants. When we zoom out from the equations and the space telescopes, This discovery connects directly to the biggest questions about our place in the cosmos. Every atom of iron in your blood, every bit of carbon in your DNA, and all the oxygen you're breathing right now was forged inside ancient stars and scattered across space by galactic winds. Those same winds were shaped and guided by the immense energy pouring out from rapidly spinning, supermassive black holes billions of years ago. Without the violent energy released by spinning black holes, the gas in early galaxies might have collapsed too quickly into useless dead stars, or it might have blown away entirely before complex solar systems like our own could ever form. In a very real and profound way, the gentle stability of our solar system today is a direct result of the violent, chaotic engines that stirred our galaxy during its ancient youth. We are standing on this planet today because the universe found a way to balance these cosmic monsters. These discoveries remind us of how much there is left to explore. We live on a tiny, fragile blue rock drifting through an ocean of space, yet human curiosity has allowed us to build instruments capable of measuring the spin of an invisible giant billions of light years away. It shows that our quest to understand reality is only just getting started, and the deepest secrets of space are waiting for the next generation of curious minds to uncover them. If you enjoyed diving into this incredible space mystery, please take a moment to subscribe to the channel, click the bell icon for notifications, and share this video with a friend who loves science. Drop a comment below answering our question about whether you think we will ever harness energy from a spinning black hole, and tell us which cosmic topic you want to see us explore next. Thank you so much for watching, and keep looking up at the stars.